I was talking last time about the possibility that quantum gravity might be what is sort of the needed thing in order to explain the reduction part of quantum theory. And I mentioned this sort of experiment where one might have a lamp, a half-silvered mirror, and a photocell. And if one goes in the forward direction, then the rule which tells you that given that the lamp emits a photon, and you ask the question, what's the probability that the photocell receives a photon, then you can use this miraculous rule of quantum theory, which tells you that you square amplitudes to get the probabilities. And you don't need to know all sorts of details about the situation. What's miraculous is that this simple rule gives you the correct probability. In this case, it would be a half. Whereas if you ask the question in the reverse direction, that given that the photocell receives a photon, what is the probability that the lamp emitted a photon, then the answer is pretty well 1 rather than a half. Whereas if you tried to apply this rule here, you would get again that the amplitude was 1 over root 2, and that the squared modulus of this amplitude would be a half. And if you try to use this rule, you will get a half for the probability that the photon came from the lamp. Whereas that's not the correct answer. The answer is much nearer to 1. And whatever it is that governs the probability here is a much more complicated issue, depending upon things related in particular to the second law of thermodynamics, which would tell you that it's very unlikely that things would just conspire to eject a photon out of the wall here just in order to produce the signal here. So what I want to try and do is to show that there is some kind of balance between these two things, that the probability in the forward direction, which is this thing we're trying to get hold of, the quantum mechanical reduction process, and I'm trying to convince you that that has something to do with quantum gravity, and to balance that against the backward probability, which is something to do with the second law of thermodynamics. And what I'm trying to convince you first is that the second law of thermodynamics is a quantum gravity problem. That if we want to understand the second law properly, we have to understand quantum gravity. Now this is presumably not a familiar point of view to most people. May seem a little strange that one has to bring in quantum gravity to describe the second law of thermodynamics. But I want to try and convince you that that really is the case. And let me remind you, first of all, with a simple picture about, well, let's take it to here. Second law of thermodynamics in its crudest form tells us that if we have a sequence of pictures like this, that the time direction is this way and not this way. And we relate this to the fact that the entropy for the glass sitting on the corner of the table is lower than the entropy when the glass is on the ground and smashed and so on, with the wine spread out all over the carpet. And we can understand the fact that entropy increases in terms of this sort of Boltzmann picture. This is the phase space of the situation, and we coarse grain that by lumping together into one compartment all the different detailed microscopic situations which we regard as the same from the macroscopic point of view, so that if we're just interested in macroscopic parameters, then we would lump these all together and consider them as the same state. Of course, this does involve a certain amount of subjective opinion. Some people might have more detailed descriptions than others, and so the compartments would not be drawn in quite the same places. So there is something genuinely subjective about this whole idea. However, the fact is that entropy works very well in practice, and this seems to be related to the fact that in practice the differences in the volumes that one has are absolutely enormous, and it's rather insensitive to differences in opinion that people might have as to where to draw these different boundaries. And the way one understands the second law is if you say this phase space point starts off in some volume somewhere representing this initial state, some fairly small volume, and then if you just ask for the most probable route that this will follow, practically not involving any other physics, but just knowing that this path will wiggle around in some fairly random looking way, then the chances are, of course, that it will enter larger and larger volumes. And because the larger volumes are so much larger than the smaller ones, once you've got into a larger one, the chance of finding a smaller one again can be effectively ignored. And finally, the phase space point will find itself in the largest volume of all, which represents thermal equilibrium, but it may take a long time to wander its way into that region there. And so, if you like, one can understand the second law in these very simple terms. It's just this question of this phase space point getting naturally enough into these larger and larger volumes, and they are enormously larger, and of course one has a logarithm in this expression here. This is the logarithm of the volume, the phase space volume in question, which gives you the entropy, K being Boltzmann's constant. And these logarithms make these enormously different volumes look reasonably respectable in terms of an entropy value. Now you might say that's all there is to the second law, but that would be very misleading, because if you try to use the argument in the reverse direction in time, you see what it tells you is, here's now, and this phase space point is somewhere or other, and if you ask for the most probable way it will move in the future, it will be indeed that the entropy goes up. But if you try to ask the question in the reverse direction, you say, given that the state is this, with the glass poised on the edge of the table, what is the most likely way for it to have got there? Not you're asking what the most likely thing for it to do, but the most likely way for it actually to have got on the corner of the table. And you look at this argument here, and you say, what is the most likely path? Going backwards now, extrapolating into the past, and you find just exactly the same sort of argument, that it must go into larger and larger volumes, which tells you that the most likely way that the glass got poised in the corner there was that it started off like this, with a great mess on the floor, jumped up, and collected onto the corner of the table. Of course, this is not what we experience in our actual world. And if it did that, it would actually violate the second law. You see, here's our picture. Instead of, I hope you can see that yellow dot, instead of doing this, what it actually does, if you go into the past, the entropy comes down. Our prediction, according to this picture, would be that the entropy would go up in the past. That's the most likely way to have reached this point here, was that it started here and came down. In other words, this, and this. But of course, when I say that, you laugh quite reasonably, because this isn't what happens. And so we realize that we haven't, in fact, understood the second law. We haven't understood why the second law also held in the past, not why it is going to hold in the future. And what's wrong with the argument, basically, is that, I mean, it's fine if there's nothing else in the problem. But what there is in fact something else in the problem. There is something which, for some reason, in the remote past, pulled this curve down to a very small value in the past. And if we believe that the second law held to the beginning of time, we must believe that you can take this curve back as far as the Big Bang, and that is, there must have been some constraint at the very early stages which caused this curve to be way down here instead of up here somewhere. Well, if we're going to try and understand this, one thing that we do have to consider, of course, is that the universe, according to standard cosmological theory, was very small in the early stages, and perhaps one can understand the fact that the entropy was small because the universe was small. And a picture something like this, actually I think I'm going to, for the moment, cover that part up too. We don't know whether what the universe will do in the future, but the picture would suggest itself that perhaps the entropy was very small because the universe was small, and that there would be some kind of ceiling on possible entropies, and that all the time the universe is trying to catch up with the ceiling, but it lags behind, and that one might be able to understand the second law this way. However, this isn't really the explanation, because, for example, the universe might be closed. It might not, of course, it might be open, the argument will apply in a slightly different form if we consider that the universe is open, but just for the sake of discussion and making things easy, let's suppose that the universe is closed, and then it will get smaller again in the future, and then you see that provided we believe that the second law holds right into the future, and there's nothing wrong with it holding, there's every reason to believe that the second law will continue even if the universe starts to recollapse. It's certainly the most likely thing for it to do, and you find that instead of the entropy being constrained to some small value, it simply has gone up and the universe catches down with it. I mean, this yellow line, as I say, it's a putative maximum entropy. It's actually not correct. There isn't any such yellow line. The entropy does keep on going up, and there is no reason why, having a small universe, the entropy should be small. But in order to understand why this is the case, we need really to understand the gravitational contribution to entropy. Now, I'm not going to be precise about these things. I'm not even going to define gravitational entropy. I'm just going to be rather qualitative about these things, and that's really all one needs for this discussion. And you see, I've just been discussing entropy in sort of situations where gravity is not involved in an essential way. You could, for example, have a gas in a box, and one's familiar with this type of discussion. If the gas is all tucked up into one corner, that represents a low entropy situation, and the thermal equilibrium case, the gas will be more or less uniformly spread over the box. So entropy increasing will correspond in particular to a spreading out of the gas. Whereas if these were not particles of a gas, but gravitating bodies, stars or something like that, then there is this attracting force, the gravitational force, which is a universally attractive force, and it tends to mean these things will clump. And so the increase in entropy will actually be accompanied by a clumping of the particles. Also, they may in fact form black holes. This is going to be an important ingredient to the discussion, that the greatest entropy of all is achieved when these bodies collect together and form black holes. And I've put a red mark at the middle here which indicates the black hole singularity. So we see that entropies increase in this direction when you get more and more clumping, if we consider the gravitational contribution. These two things may, of course, occur together, and it's a question of balance, what in fact happens when the entropy goes up. But if we consider the universe as a whole, and let me talk about, well, either the possibility of a closed or an open universe. This was the situation I was thinking about in the case of a closed universe, where you start off where the gravitational contribution, for some reason, is initially very small. You have a universe, just from observationally, the universe seems to have been very uniform in the early stages. The black body radiation tells us that, indeed, the universe was not clumpy in the early stages, not particularly clumpy anyway, very, very smooth. And the clumpiness in the universe seems to be a feature which has come somewhat later. So that there's this kind of thing going on. As time increases, you do get an increase in entropy, but the thing is that the entropy increase in gravity is possible because for some reason the gravitational contribution to the entropy was held down in the Big Bang to a very small value. So one has, just comparing these two pictures here, we have this initial Big Bang which overall is small entropy, and at the end you have a great mess of a singularity which involves the congealing of many, many black holes. So you get these black holes forming here, and they congeal into a great mess at the end. And the increase in the entropy, the major part of this entropy is in fact in the black holes. You find that I'll give you some figures in a little while, but we do find that the major part of the entropy is in black holes, and the increase is, as far as gravity is concerned, can be understood in these terms. Now, this is a sort of spatial picture of what happens. You see here is the universe uniform. Of course, it's very hard to draw these pictures normally because this is the whole universe. You see, there's nothing out there. And so that's the whole universe. But eventually these things clump and recollapse and form a great mess. And all the time the entropy is going up, primarily because of the clumping that one has in gravitation. Now, in the open case, I should just make a remark about this, you still have the formation of black holes, and the major part of the increase in the entropy arises from gravitational clumping as before, and the forming of these black holes. There's an additional complication in that one has to worry about Hawking evaporation. Eventually these black holes will tend to disappear because they're not totally, because of quantum effects, they radiate, and this radiation could eventually cause them to shrink away. However, the time scales involved, even for the smallest of black holes, which are things of the order of the mass of the Sun, will be something like 10 to the 56 times the age of the universe so far. Of course, they may, for an infinite open universe, you expect to find larger and larger black holes, so these will take much longer to disappear, and these will still persist. I imagine it may be that some of these things will persist forever, because, well, I'm not sure, that's a delicate calculation. Whether the bigger the universe, you expect bigger black holes, and whether they will persist longer than, whether there'll still be some left at the end, I'm not even quite sure about. But that's not important, really. The main point is that the entropy does go up because of the formation of black holes, and it's simply not correct to regard going back to this picture here, regard there as being a ceiling on the entropy. This just isn't correct. If you take gravity into account, the entropy is not small because the universe was small. The entropy was small because of some very special feature of the universe in the early stages, which corresponded in some sense to the gravitational contributions to the entropy being, or the gravitational degrees of freedom somehow being held down. And because of the weakness of the gravitational coupling, it takes a long time, because these, in a sense, thermalize. Thermalize is perhaps an inappropriate word, because it doesn't look very thermal here, but that's, strictly speaking, what is happening. The gravitational contributions take a long time to thermalize, and when they do, you end up with this mess at the end, or this mess here. I want to say a little bit more about general relativity and space-time geometry to try and understand what the nature of this constraint is which occurred at the Big Bang. And I just give you some sort of simple discussion here. We won't need very much general relativity. All we need to know is that there is a thing called the curvature tensor, the Riemann curvature tensor, and this can be split into two parts. One part comes from the Ricci tensor, the contracted Riemann tensor, and this is the part which, according to the Einstein equations, is identified with the energy momentum tensor, or the trace reversed energy momentum tensor of matter. And you can make this look like something with the symmetries of a Riemann tensor by putting the metric in and sort of churning the indices around appropriately. This is the Ricci part, and then you subtract that off here, and what's left is called the Weyl curvature. The Weyl curvature measures the conformal part of the curvature of space-time. But one can understand these in fairly simple-minded terms in the following way. To understand the physical meaning of the curvature, what one can do is imagine a set of particles. You see, imagine yourself out in space here, falling freely. If you prefer not to fall towards the Earth, you can imagine yourself in orbit around the Earth, and surround yourself by a sphere of particles. And that sphere of particles you initially hold at rest, and then you let go and see what happens. Well, even on just simple Newtonian terms, we can appreciate that there will be a distortion of this sphere of particles. Well, these particles are accelerated towards the Earth's center slightly more than you are, these ones slightly less, so they will accelerate away from you. The particles at the side here will accelerate inwards towards the Earth's center, because the Earth's center, of course, is not at infinity, so these particles will, with respect to you, accelerate inwards. So what you see is that this sphere around you, which you just hold at rest initially, accelerates into this ellipsoidal form. And this, in fact, is the tidal effect of gravity, and the word tidal is used, of course, because it's precisely the effect that the tides... See, if you imagine the moon was down here, and this was the Earth up here, and this was the water, there was the water on the Earth, then, of course, it bulges out in the direction of the moon and in the opposite direction, and this is precisely the tidal effect caused by the moon. But now we're looking at it as ourselves in orbit around the Earth, and the Earth is causing this tidal effect. And this tidal effect, since we're in empty space, the Ricci tensor is 0, is the effect of the Weyl part of the curvature. And the thing is that the Ricci part is the part which causes a volume change. If you're in empty space, then the volume of this ellipsoid here is the same as the volume of the sphere that you start with. And the volume preserving distortion effect is the effect of the Weyl curvature. When I say volume preserving, this is only the first term. Once the thing starts to move, then there are nonlinear terms which sort of spoil this a little bit. But as far as the leading term is concerned, it is simply the volume preserving effect, which is the Weyl curvature, and the Ricci curvature measures the change in volume. So what I'm thinking of here now is a slightly different picture. If this sphere of particles was actually surrounding matter, and let's put the whole Earth in there just to make it more dramatic, then the acceleration, as you can see, will be inwards all the way around, and so you have a volume reduction effect, and that volume reduction effect is due to the Ricci tensor that is present in the Earth. And all that I'm saying here is true in Newtonian theory as well. In fact, Newtonian theory, in fact, it's a lot clearer than in the general relativity case, but the problem is that the situation is basically the same. So one can understand these two parts of the curvature. This part is the distortion effect, and this is the volume changing effect. It's not totally clean, this division, because there is actually a distortion effect due to the Ricci tensor as well, if there's motion involved here, but this is effectively the way one can understand these two parts of the curvature. Now let's understand that what happens in terms of matter and clumping and so on. If you had a uniform distribution of matter, then you have no Weyl curvature. This is like the universe in the early stages. This model here, the Weyl curvature is 0, but you still have a lot of Ricci curvature. And when things start to clump, if you like, the Ricci part has got more concentrated, but roughly speaking, there's the same amount as you had before, it's just more concentrated. But now you find that there's Weyl curvature in the region which surrounds this clump here, and the more concentrated this clump is, the larger the Weyl curvature will be. And in the final case, when you collapse to a black hole, then the Weyl curvature actually diverges to infinity as you approach the black hole singularity. So if you like, you can understand the difference between what's happening here and here in these terms. Initially, you have a universe which seems to be very uniform, and where the singularity here is indeed a singularity in the curvature, but it's a singularity in the Ricci curvature. And what one can apparently understand the constraint in the initial Big Bang by saying that the Weyl curvature, for some reason, seems to have been either very small by comparison with the Ricci tensor, or perhaps simply 0 in the initial stages. And the simplest assumption would be that the Weyl curvature just starts at 0. That's a huge constraint on the initial state. And if you now compare that with black holes or the final singularity, you don't have this constraint. It's the Weyl curvature diverges and completely dominates the singularity in the final stages. I should make a remark about black holes. You see, these are all meant to be black holes here, and they're all congealing at the end. This is just a space-time diagram of a black hole. Matter collapsing initially, singularity at the center, time going upwards, and this is the horizon here, where signals initiated inside the horizon cannot escape to the outside because the light cones are all tipped over like this. And here we have two observers, one falling in and the other remaining at a safe distance. And you see that the photons from the observer falling in take longer and longer to escape. And when this observer is inside, these photons can't get out at all. So this is the collapse to a black hole. And one finds, at least in the exactly spherically symmetrical case where one can look at it explicitly, that the Weyl curvature diverges to infinity in the center. You have Ricci curvature here where the matter is present, but after a while that all gets collapsed away into the singularity, and you have empty space, and the singularity here is entirely of the Weyl type. In the general case where there are perturbations, one expects something rather similar. The Weyl curvature one expects also to diverge to infinity, but perhaps with a much more complicated and oscillatory components and so on. Much more complicated, but nevertheless infinite Weyl curvature here. Now we can compare this with a white hole. A white hole is just the time reverse of a black hole. So you could, in fact, if you like, just turn the picture upside down, but it's perhaps clearer to draw it again because I put my light cones poking into the future here. And the white hole is just a hypothetical thing. You would have a singularity initially, and then at some moment of its own choosing, you would have matter exploding out. And, well, these are not very nice things to have in a universe, although some people like them to try and explain things that they can't explain in other ways. The particular reason that they're not very nice is that they violently disagree with the second law of thermodynamics. And so they're not things that we really would like to have in our universe from the point of view of thermodynamics. If we expect a second law, we don't expect white holes. There is a relationship between the surface area of the horizon and the entropy. I'll come back to that. But according to the formula due to Bekenstein and Hawking, the area of this event horizon is a measure of the entropy in the black hole. And there's also a theorem which tells you that this area is something which increases, and that's consistent with the second law, whereas for a white hole, the area would decrease, and that would be violently inconsistent with the second law. So we don't like these things, we like these. Now, of course, I've been talking about gravity a lot, and one might ask, what's this got to do with the kind of entropy that we're familiar with, and you stir your coffee cup and things like that, that's always talked about in connection with entropy. I just want to explain that it has everything to do with it. For example, you might have this glass of wine poised on the corner, and you might say, well, that's got to do with gravity. Well, you see, if you ask, how did it really get there? It really got there probably because somebody put it there. And somebody put it there because somebody was around and able to do things and alive and so on. And that person was alive because that person was able to eat and breathe. And that person was able to eat and breathe because of the fact that there are animals around, and animals because there are plants around, and ultimately because of photosynthesis, which did this entropy reducing trick of converting, in effect, carbon dioxide into carbon and oxygen, which could be recombined again, and that's how we managed to keep ourselves alive. And this happens because the sun is there, or more particularly, not because the sun is bright and so on, but because the sun is there and the dark sky is also there. You need both of the things. If you simply had a uniformly bright sky with the sun all over the place, that wouldn't be any use to you at all. And although people often talk about our getting energy from the sun, that's not what we get from the sun, because in fact the Earth spews all the energy back again into space. What we get from the sun is a source of low entropy. The energy from the sun is in the form of a comparatively small number of high energy photons, that's visible light, and after all this rigmarole, it gets thrown back out into space again, essentially in the form of infrared radiation, which is a much larger number of lower energy photons, so the total energy coming in is equal to the energy going out, but you have many, many more degrees of freedom going out because you have more photons. And so you're making use of this vast increase in the entropy which is available because of the sun being a hot spot in the otherwise dark sky. So it's everything that we know that why we're making use of the entropy. Well, there are other things like which I don't want to go into, like thermonuclear sources and so on, which ultimately again come from stars which explode and so on, but that's all part of the same story, really. When I say the same story, I mean you have these stars around. and you have stars around which shine in an otherwise dark sky. Well, you might say that's all to do with thermonuclear reactions and so on, which of course it has to do with, but the basic point is that the sun is there at all. And it's there at all because it was able to condense out of a previously diffuse gas into this body. And it did that because gravity was available to allow it to clump out of this otherwise diffuse gas. In fact, if it weren't for the thermonuclear reactions, the sun would simply get a lot hotter. It would die out more quickly too. It wouldn't be very suitable for life on the Earth, and so we're grateful to the thermonuclear reactions for keeping the sun in the form that we like it to be. But the essential point about why this process can take place at all is that gravity was there available to enable the previously uniform distribution of gas to concentrate into these hot spots. So here we have, this is what I was talking about before, because of gravity, gravitating bodies, you gain in entropy by clumping. And it's because the entropy was set for some reason to be low in the initial stages. Well, I can show you the picture I showed you before last time. It's essentially the same thing. Thinking about the closed universe again, just for convenience. The universe was for some reason held in this very special state. And here I have this picture of the Creator producing this universe rather than this one, which would occur if the Creator missed, which wouldn't be any use to us at all, full of white holes and no second law of thermodynamics. Now, I put this figure down here of 1 part in 10 to the 10 to the 123. You might be curious to know where that figure comes from. So let me try and show you how one computes things like this. And the crucial thing in the calculation is the Bekenstein-Hawking formula for the black hole entropy. And this is the formula here. The entropy of a black hole, that's BH, stands for black hole, or if you prefer it, it stands for Bekenstein-Hawking. And A is the surface area of the horizon. These things here are just various constants. That's the velocity of light, that's Boltzmann's constant, the gravitational constant, and Planck's constant divided by 2 pi. Of course, if you're a theoretician like myself, you put all these things equal to 1. There's a 4 down there which you're a bit stuck with, but nevertheless, essentially it's A, which is the formula. Now, you can put all these constants in if you like to see the scale of this sort of thing. And just to show you what these figures look like, let's consider a closed universe with 10 to the 80th baryons. That's just a convenient figure. Of course, it's also more or less the figure that Eddington at one time said the number of particles in the universe ought to be. Nobody believes that anymore, but it's still, the universe is presumably at least as big as that. It's just to give you some feeling for the figures here. Now, when the black body radiation was first found, people were struck by how much entropy there is in this black body radiation. And people were surprised by the size of this figure, which is that something like 10 to the 8th or 10 to the 9th entropy per baryon. So for our universe here, the total entropy would be 10 to the 88. So you'd have 10 to the 88th for the entropy of this universe, which you might think is a pretty big figure. But it's not all that big when you start to consider that there might have been black holes. In fact, it might have been the case that the entire universe consisted of black holes, each of the mass of the sun. And you notice that if that's the case, using this formula, you see the entropy has gone up to 10 to the 20 entropy per baryon, or 10 to the 100 for the total entropy. Well, you may say, of course, it's not like this, but I'm just trying to emphasize that this is a small figure when you consider the possibility of formation of black holes. But in fact, it's much more like this. You see, if you consider galaxies like our own with 10 to the 11th solar masses, say, and it could well have a 10 to the 6th solar mass black hole in its center, and you notice that because you gain a lot by having large black holes in this figure. So by having a big black hole in the middle, you can now dispense with all these little black holes and still increase the total entropy. So we've gone up to 10 to the 101 for the total entropy. Now, if this universe, when it starts to recollapse, then basically, well, let's imagine not the whole universe recollapse, but these galaxies begin to swallow a substantial part of their entire mass, and this figure now goes up enormously. And then if you want to try and estimate what the entropy of the whole universe would be when it recollapses, you can do this by roughly thinking of the whole universe as a black hole. The formula isn't quite appropriate in that case, but at least this is a reasonable sort of limit that you could imagine approaching by forming larger and larger black holes. And you see that the total entropy would be at least as much as 10 to the 123. And then when you think of the poor creator, remembering that there's a logarithm, the entropy, after all, is a logarithm of phase space volume. That's where you get this additional exponent. And so here is the figure of 1 in 10 to the 10 to the 123. Of course, the universe could well be bigger than this, in which case this is even more precision required. The universe may well be infinite, in which case this is 1 in infinity, which makes it even harder to find that point, if you like. Okay, so that's just to give you some feeling for the sort of precision that seems to have been involved in the initial singularity. Now, let me just say something about classical singularities, first of all. There are theorems which tell us that from classical general relativity we must have these things. We may not like them, but they're part of the classical theory. And you can have singularities of either, say, the initial type that we have in the Big Bang, or what we could have if we had white holes. These are singularities out of which signals or matter can come, and we have singularities of the final type, which are singularities into which things can fall, such as the Big Crunch singularity of the entire universe, if it does recollapse, or the singularities that occur inside black holes. These are all of this kind. You could also have some kind of combination of these two, things called naked singularities. The general belief is that they don't occur. It certainly makes the discussion much easier if we can assume, at least for the moment, that they're not there, in which case we only have to talk about these types of singularities. I think that's a reasonable assumption at this stage of our understanding. Now, the thing the singularity theorems tell us is that these things are features simply of general relativity and not features of the special symmetries that one tends to impose on special solutions. So what do we do with them? And there are places where the curvature goes to infinity, that kind of thing. What do we do with them? Well, what we expect is, by, if you like, comparing the situation with Rutherford atoms, where in the early days of this century one ran into a seemingly comparable paradox where the electrons would spiral into the nucleus, giving an infinite burst of radiation at the end and so on, and a singular state. And this was resolved by the Bohr atom. So what we believe is it's quantum theory, quantum gravity, in fact, which is going to resolve these problems of the singularities. That's the standard belief, and certainly I'm going to go along with that what we need is a quantum gravity theory which tells us what to do rather than throw up our hands and give up at these two types of situation. But there is one fact which is, I could say, an observational fact. It's the second law, and not just the second law, but the form in which that second law appears to be given to us, which is that we have a time asymmetry. You see, the Weyl curvature appears to be zero at initial type singularities. We can make a hypothesis, and this is what I call the Weyl curvature hypothesis. The Weyl curvature hypothesis is that, simply that this type of singularity, for some reason, which presumably comes out of quantum gravity, is constrained so that the Weyl curvature is zero, whereas this type of singularity is not constrained in any way. And that gives us a number of very satisfying implications. First of all, the second law of thermodynamics. Secondly, a very isotropic early universe, which is what we observe. Thirdly, the absence of white holes, which is all part of the second law, if you like. And probably no tiny little mini black holes, which are a theoretical possibility, but are not observed, and they may well not be present. If the universe was very uniform in the early stages, you don't expect these little tiny black holes, which could only form in the initial Big Bang. We don't expect them to be present if this initial state is very uniform. And these things are all consistent with observation, and also the second law is a very important part of physics, and somehow we appear to be able to understand where it comes from if we could understand where this comes from. And that would mean, presumably, quantum gravity. So this is really the gist of the argument. I'm trying to convince you that to understand the second law, we really need our quantum gravity theory. It is a matter of quantum gravity. Now, I just want to make a few remarks here. General relativity is time symmetrical. And what about quantum mechanics? Well, you see, the part of quantum mechanics that may not be time symmetrical is state vector reduction. You might ask that there might be some kind of symmetry breaking effect arising when one tries to quantize this time symmetrical theory, and there may be some anomalous situation arising. It's conceivable that it comes just through the standard procedure of quantization, but you have to bear in mind that we've got to violate all these things here, not just T and PT and CT. You've also got to violate CPT. Anything with a T in it has to be violated in order to explain the Weyl curvature hypothesis. My own view is that you haven't got much of a chance of getting all that without something which simultaneously affects general relativity and the very structure of quantum mechanics, and in such a way that the state vector reduction procedure, which I'm going to say a little more about, and about its time asymmetry, that this procedure is going to be part of the theory we need. So I think we need a radical new theory, and various things which I'll perhaps, I hope, have time to say about a little later. I see I don't have a great deal of time. Let me talk about the connection between the Weyl curvature hypothesis and state vector reduction. See, I mentioned at the beginning that we need perhaps some kind of balance between the forward and the backward processes here. And in fact, it seems to be possible to make this a bit more explicit. The trouble with talking about the Big Bang and all that is that there's only one universe, and it's always difficult to discuss physics when one is given only one situation. One can't talk about statistics. However, it's not quite as bad as that, and what one can do is think about a situation, a thought experiment, which I refer to as Hawking's box. This is a box here, which is a very huge box, perhaps the size of a galaxy or something. It doesn't have to be that big, but let's make it the size of the galaxy. And we put just some matter in it, perhaps about the mass of the solar system or something like that. And this box is supposed to be such that no information or no material can get in or out, no energy is supposed to be able to cross its walls. Of course, that's totally artificial, but the question is, can we make decent deductions from this theoretical situation? Now, this is supposed to be the phase space of the box. And we have to consider that there could be a black hole in the box, or there might not be a black hole in the box. And this over here is meant to be where there is a black hole, and this is meant to be where there isn't a black hole. I mentioned before that black holes represent a huge amount of entropy. So you might expect an enormous volume over here corresponding to the entropy of the black hole. Now, the Hawking effect, which is all part of the Bekenstein-Hawking formula, tells you that there is a certain amount of radiation associated with the black hole. And so for real equilibrium, it has to be in equilibrium with radiation of the appropriate temperature. So over here we just have radiation, that's when there's no black hole, thermal equilibrium apart from the fact that we don't have a black hole. And over here we have a black hole in equilibrium with the thermal radiation. Now, the thing is that if we follow the flow lines over here, and if you make the assumption that the Weyl curvature hypothesis holds, which is, I should say, a time asymmetrical assumption, we just assume that. In fact, if you don't make this assumption, it's hard to know what to do with the white holes. In fact, there are very serious problems in understanding what happens here if you allow yourself white holes. But if we say white holes are excluded because of this Weyl curvature hypothesis, then we get a curious phenomenon, which is this kind of destruction of phase-space volume. And I want to try and explain that. It's all part of the Hawking phenomenon. I've just drawn some pictures here. Here is the Hawking process. You have collapse to a black hole, radiation coming away, which you can think of in terms of pair creations from out of the vacuum, and then the black hole, since particles can have negative energy inside the black hole, this can get swallowed up and releasing a real positive energy particle to infinity. So one can understand Hawking radiation in this sort of crude way. and if there is no material outside, this black hole would eventually radiate itself away completely, presumably, and disappear, although the physics that goes on here is really total hand-waving. But nevertheless, that's the sort of picture that seems plausible. Now, I've tried to redraw these pictures in the form of conformal diagrams. This is where you rotate the light cones and turn them so that they point up at 45 degrees. Makes the discussion rather easier, and then you can put infinity in as well. So this is past null infinity, future null infinity. This is after the black hole has disappeared. That's the singularity. It now turns up and looks horizontal. It swallows up the matter that hits it and so on. And that's the symmetry axis here. This is the symmetry axis again after the thing has disappeared. This is if we don't take into account the final disappearance of the hole, and in fact the Hawking calculation really is done in terms of this figure here. You're not really concerned with the back reaction on the black hole itself. You're just looking at a situation in a curved background. You're trying to do quantum field theory in a curved background. And this is the gist of the Hawking argument. This is just this diagram again. This is the horizon. This is future null infinity, past null infinity, and this is the singularity. This sort of, well, you consider massless fields on this background. They could be, if you like, photons or weak gravitons, if you like, and we're going to ignore the back reaction on the space-time. And the way the calculation proceeds is you consider the Fock space of the incoming states here, and when I say sort of this twiddly equals, that really means there's a sort of Bogoliubov transformation between this and this, but these are, information here is equivalent to this, and this says that this information, that going on here, is equivalent to this together with this. So horizon information together with infinity information. And the horizon information is equivalent to the singularity information, but it's just harder to talk about. So we have this kind of equivalence here. And the thing is that the information is actually lost. It gets absorbed into the singularity, and so what one does is to trace over these states. And you start off with a pure state. This will evolve by tracing over this internal states here into a density matrix. This is sort of a schematic indication of the tracing over the states to give you a density matrix. And the Hawking evaporation, the Hawking radiation can be understood in this way, and it turns out to be a thermal radiation. Anyway, this is the way the calculation is done. What I want to emphasize here is that you lose information on the singularity. And this losing of information occurs in one direction in time, and that's where this congealing of flow lines occurs. You have more information here to distinguish the states. Finally, you have less information because you throw away the information that's absorbed into the singularities. And you have congealing of flow lines and not production of flow lines, because the Weyl curvature hypothesis tells you you have this type of singularity that absorbs information. You don't have the corresponding thing with these in the past, which would produce information. So now you ask, if we have the Weyl curvature hypothesis tells us that we have destruction of flow lines, and you consider the whole situation, there seems to need to be, to balance this, the production of flow lines. And what I'm trying to say is that production of flow lines is what comes about in state vector reduction. That there is a balance between these two things. State vector reduction balances the Weyl curvature hypothesis. And it seems to me that one could make a genuine quantitative comparison here. I find that it's actually rather difficult to do the calculation because it's rather hard actually to calculate how much information gets lost here and so on. But it's showing you that it must be a gravitational effect if you accept this whole argument here, and then one is led to this sort of picture that I was talking about yesterday. The suggestion is that reduction takes place when the geometries to be superposed differ by a quantum mechanically significant amount, say something like a graviton, which would be a longitudinal graviton, presumably. And this tells you expect to see effects at something like 10 to the minus 5 grams or so. And see the forward direction, the probabilities are given here. The fact that this outcome and that outcome can arise, that's the splitting of the flow lines, and the backwards direction, you have to trace the other possibility right back into the initial singularity because it's involved with the second law and so on, and that's the balancing effect of the reduction of the flow lines here. Anyway, that's just the general picture, and one of course needs a general theory in order to understand these things, and I don't have a general theory. Well, I want to end by making a number of comments, and I suspect I'm going to need a little bit more than than the time I have allotted, but let me just try and say... Okay, thank you. I want to say two things. One is, well, I say two things, they're two fairly long stories, but one of them has to do with quantum theory and the mind. This is a very long story, but we don't know much about it. These ideas have been around for a long time, that perhaps quantum indeterminism gives scope for free will. Another connection between quantum theory and the mind, has been suggested particularly by Wigner, is that it might be consciousness which reduces the state vector. Now, as you can see from the kinds of arguments that I've been presenting, I don't think it's consciousness that reduces the state vector, I think it's quantum gravity. You might think that's just as bad, but nevertheless, it's at least physics. Nevertheless, I do think that the mind is relevant to this whole issue. And my point of view, which I tried to explain in my book, is that state vector reduction, although it's a purely physical phenomenon, conscious beings are conscious by virtue somehow of their ability to harness a non-computational ingredient of the theory that we're seeking in R. Now, we don't have this theory, so we don't see why it's non-computational. So there are lots of, guesses involved in this. But what I want to try to persuade you is that in conscious phenomena there is something non-computational. So we want to try and see what in physics, where can we find something non-computational in physics? And my suggestion is that it has to be in this reduction process. But really, the real question I want to address here is, what reason is there to believe that there must be something non-computational in conscious thinking? And when I say computational, I really mean anything that could in principle be carried out by a general purpose computer. And this means carrying out an algorithm, Turing machine action, and I really want to include various things that sometimes people don't use the word algorithmic for, things where the word heuristics is used. Of course, parallel computers is nothing effectively different here, or neural networks, essentially learning devices. But anything which could be simulated on a modern general purpose computer is something which I'm calling computation. Now, in effect, it includes things like random elements, because you could have, this is in effect, strictly speaking there might be a difference, but you can certainly do things which look random by introducing pseudo-random numbers. And then there's the question about the environment. Is it possible that the environment introduces some non-algorithmic ingredient? Well, it is possible, but really if you accept that, then you're basically accepting my thesis anyway, that there is something non-computational going on in physics. If you cannot simulate the environment in principle, then there is something non-computational in physics. And this is, in effect, what one is trying to establish. Now, let me try and present an argument to show that there is something non-computational in conscious thinking. And I'm only going to restrict attention to a very small part of conscious thinking, namely what mathematicians do when they try and prove theorems. Well, proof theorems is slightly begging the question. When they try and see what's true in mathematics, I should put it perhaps more like that. And I want to give you some examples of computations, certainly computations, but the point is that not all computations come to an end. And here are two examples of computations that would not come to an end. The first one is obvious. So you find an odd number that is the sum of two even numbers. And you could set your computer to try and find an odd number that is the sum of two even numbers. Well, of course, I hope everybody here realizes that that poor computer would go on forever, or until it breaks down or something. Another example, less obvious, find a number, and when I say number, I mean a natural number, 0, 1, 2, 3, 4, etc., that is not the sum of four square numbers, and this is a famous theorem due to Lagrange that this calculation never terminates. This is easy to see, this is much more difficult to see. So the question is, in order to see such things, what procedures do mathematicians use? Do they use algorithmic procedures? Is it simply the enacting of some algorithm? or is it something that's not an algorithm? Well, in order to try and understand this, I want to generalize this slightly. You have to really, for technical reasons, to talk about families of problems. And so instead of just saying 2 here, I'm going to say n even numbers. And this stops for no n, of course, just as obvious. Find a number that is not the sum of n square numbers. That stops for 0, 2, 3, 1, 2, 3. See, 7 is not the sum of 3 square numbers, but it is the sum of 4. Lagrange tells us that every number is the sum of 4 square numbers, so this calculation will not stop for any number larger than 3, but it does stop for 0, 1, 2, or 3. Anyway, so that's just examples, and the question is, when mathematicians convince themselves that such and such a calculation will not stop, are they using an algorithm? And I'm going to give you a simple argument which suggests that they're not. First of all, you can list the calculations. These are just computer programs, if you like, and you could certainly list them in some order. There's no problem there. Order of length, and then alphabetically or something, or numerical order. Some sort of numerical order is all you need here. But it has to be an ordering which is effective. That is to say, you can tell, given the number down here, which calculation it is that it's performing. But that's no problem. Now I want to consider, suppose you had a stopping deciding algorithm. That is to say, A is supposed to be an algorithm which, if it successfully completes, if it finally works itself through, it says, yes, this calculation doesn't stop. So this is a means of deciding that certain of these calculations don't stop. I'm not asking that it always works for all calculations. I'm only asking that when it does work, that is, comes to an end, it is giving you a convincing demonstration that this particular calculation doesn't stop. And notice it's a function of 2 arguments. And so A of p and n tells us that Cp n does not stop. Now the trick is to put n equals p, and now you have an algorithm. See, A is meant to be an algorithm or computation. This is a computation which now depends only on one number, so therefore it is one of these things here. And let's say it's the kth one. So this tells us that, if we just look at this line here, in the particular case when p equals n, tells us that a n n stops. If that stops, then it gives us a demonstration that c n n doesn't stop. Now let's put n equals k and ask whether a k k stops. Well, if a k k does stop, then we see from this line here with n equals k that c k k doesn't stop. But notice from that line that a k k is the same as c k k, so therefore we know a k k doesn't stop. So if a k k stops, it doesn't stop. Well, that's all right. It just tells us this is the right answer. It doesn't, in fact, stop. That's correct. And we've just seen this, you see. I've just shown you. We see this provided we know that A doesn't make mistakes, and that's critical. It might be that A sometimes makes mistakes, but if we believe A, then we know it doesn't make mistakes, and so we see that AKK doesn't stop. But you see, A doesn't see it, because A is a procedure for deciding that these things stop, and we've just shown it doesn't stop. So by this argument, we see that A doesn't stop, AKK doesn't stop, but the procedure A doesn't. So what this is roughly speaking telling us is that we aren't using A to decide mathematical truth, whatever A is. So what it tells us, and this is not, there's a lot of arguments about this kind of thing, but what it certainly tells us is that mathematicians are not using a knowably sound algorithm to ascertain mathematical truth. So if you knew what A was, and you knew it was sound, that would be a contradiction. And that is certainly a contradiction. So mathematicians are not using a knowably sound algorithm to ascertain mathematical truth. This was certainly appreciated by Gödel way back in the 1930s. However, they might be doing all sorts of other things, you see. They might be using an unknowable, horrendous unknowable algorithm X to ascertain mathematical truth. They might be using an unsound algorithm, an algorithm that makes mistakes. I think this was Turing's view. It's not so unreasonable, but I want to try and argue against it in a minute. We might be using an ever-changing algorithm. I think that's cheating, really, because if the algorithm is changing, how is it changing? you see. Either it's changing because of perhaps random elements or the environment, and as I said before, random elements just by itself seems rather implausible because you can certainly imitate them very closely. I mean, it's a possibility. The environment, well, we're trying to show that the environment, that something is non-algorithmic in physics anyway. You might resort to mysticism, which I believe was more or less Gödel's solution. These were certainly things that were familiar to people in a certain way, and he tended to think that the mind was something beyond the brain. If you believe that we have to understand minds in terms of physics in some way, although it's not physics that we can understand yet, then one seems to be driven, perhaps, unless you believe in X or Y, to some kind of non-algorithmic physics. And that's my own view. I do want to make a remark about X and Y, and this is that truths found by the mathematical community are, first of all, extremely reliable, and secondly, very remote from experience. And so it is rather a remarkable fact that, see, if somehow, how did the mathematicians manage to get this very reliable way of understanding mathematics? They certainly do make mistakes, but the point is that mistakes are correctable. You can root them out and they're recognizable as mistakes. The mistakes are not things that, everybody is sort of simultaneously blind to. They're recognizable as mistakes. And remote from experience, well, you see, how could natural selection, which was presumably interested in building creatures that could, build good mammoth traps or something like that, they weren't interested in mathematics that was very sophisticated and remote from experience. They were interested in practical things. But it does seem to me that the very quality of understanding, whether it was for deciding, what kind of mammoth traps would be effective at catching mammoths, if they stood on this thing and this thing goes up and down, the mammoth goes, you see, that kind of understanding, you see, that general quality of understanding, which is the same quality, which I claim is that we use all the time in understanding mathematics, as would have been good in things that were needed for natural selection. So that's my point of view, that there is something in what we do with our conscious understanding which is not algorithmic and cannot be understood simply in computational terms, therefore. Oh dear. Well, I just want to show you that it is possible. You could have a physical system which is not algorithmic. I want to indicate that these determinism and algorithmic nature of a physical model are totally, or not totally different, but they are certainly different things. And this is just to show you, you could have a toy model, of course not a realistic model, where you could have a number pair describing the universe, two natural numbers, and the state of the universe at the next instant of time is, if it's pq now, it's p plus 1q at the next instant. If cp of p stops, and it's q plus 1p if cp of p doesn't stop. And notice that this is an entirely deterministic model. However, it's not a computable model. I just want to show you that computability and determinism are different issues. And my own opinion is that this non-computability will come in the new sort of theory that we need in this thing here. Could I take a few minutes just to describe one other thing? This is, I can't give you a theory, of course, which does this, but I do want to make a few remarks about where I personally believe a very fruitful place to look would be in looking for a new theory. And this is something I've been working on for a long time, and I can't do it justice in just a few minutes, but I think it's worth making a comment because it relates to things I was talking about earlier. One was this intimate relationship between the complex amplitudes and spatial geometry. And I indicated this Riemann sphere tells you that we have somehow a very intimate relation between these funny, curious, complex amplitudes and something to do with geometry. So when I say quantum gravity, we're looking for some theory which unites quantum theory and space-time structure in a very intimate way. And this is one of the most intimate ways in which space-time structure and quantum theory are related. There's another way in which space-time structure is related to the Riemann sphere, which is also very striking. And now the sphere I'm going to think of as the sky. If you imagine yourself out in space looking out at the sky, you see a sphere. And I'm going to think of that sphere as the Riemann sphere, the complex numbers together with infinity. And the transformations of that Riemann sphere to itself, which preserve this structure as a complex manifold, are precisely the bilinear transformations in that complex number, and they are precisely the transformations of the Lorentz group, or the reflection, non-reflective part of the Lorentz group. So the way I like to think of things is here I'm situated out at infinity, I'm situated somewhere in space, looking out at the sky, and the different points in the sky correspond to different light rays, different generators of this light cone. And different people looking out at this same sky would map this sphere according to this complex analytic transformation. So somehow, if you think of the sky as being a Riemann sphere, or a complex one-dimensional manifold, if you like, that is consistent with the Lorentz group. And twistor theory is a way of trying to make this more global. So you think of space-time, which has points and light rays in it. You build a new space where the light rays are in effect thought of as the points now, and the points are these Riemann spheres. All the light rays through a point correspond to a Riemann sphere. So somehow this space is a sort of complex space, and I'll say a little bit more about that. But the point is that you have this complex structure built into the geometry at a basic level, and you also have a sort of non-locality built in, which I think is important from the EPR type of things we're talking about. Can one understand space-time by turning things all inside out somehow? The non-locality, which is so puzzling, has to do with thinking of points as things separate from each other. Whereas if in some way it was the entire light rays that you thought of as the basic ingredients, then there is a kind of non-locality built into one's description right at the beginning. Now this is a rather vague statement, and to make that into a theory, which actually makes sense of this kind of thing, is a big, long job. But nevertheless, it is a framework which would allow you, in principle, to discuss space-time in a non-local way. So here one has twistor theory, light rays, and I put a little spiral around it because to make it more accurate, these things actually involve the spin of the photon as well, and you need that in order to get a genuinely complex space here. This complex space is actually a complex projective three-dimensional space. The points correspond to these spinning photons, and the points here correspond to these Riemann spheres, which are actually straight lines in this space here. And it's non-local, it's fundamentally complex, and it's also mathematically sophisticated. I said something about the angular momentum here. If you like lots of equations, you see this is actually how you do it. This is the momentum and angular momentum of a massless particle, and these z's here are the components of the twistor, and to give the space I was talking about here, you look at the ratios of the z's, and that gives you this space here. So that's how you start. Well, that's how you start. Well, let me just make a remark here. One thing that makes life complicated is that there are lots of different kinds of twistors. They're all equivalent in some sense, but they give you different kinds of insights. I want to mention number 4 particularly because it's something I've been thinking of recently, and it seems to give some insights. Well, let me put this is my final transparency, so you know I am actually coming to an end here. The achievements of twistor theory, first of all, most of the achievements seem to be just in mathematics. It's always a bit disconcerting. One had produced these ideas in the hope that it would give you real new insights into physics. But so far, the applications of twistor theory seem mostly to be in mathematics. Nevertheless, that's nice anyway. And there are a lot of applications in representation theory and differential geometry. I mentioned things like hyperkähler manifolds and conformal geometry, self-dual spaces, and integrable systems. One can understand practically all integrable systems in terms of actually the Ward construction for self-dual Yang-Mills fields. So integrable systems is a nice big area which is very much illuminated by the subject of twistor theory. There are certain areas, things which are not so much, partly maths and partly physics. One can understand perhaps energy momentum in general relativity in a way that one thought one couldn't understand before using twistors. These self-dual and anti-self-dual solutions of the Einstein and Yang-Mills equations. This is partly really up here. A neat integral representation, contour integral representation for massless fields. Twistor diagram theory. This is a theory which is developed particularly by Andrew Hodges, and he has some very nice ideas which give you a kind of regularization to give you finite answers in place of the infinities of standard Feynman diagram theory. So I think this is a very promising area. He's looked at things like QCD and electroweak theory using twistor diagrams. It's hard work, but it looks extremely interesting, particularly in respect of the way one gets this kind of regularization, which I think is perhaps significant. There is a program for particles, so I put lots of question marks here. The main outstanding problems are how to treat spacetimes, curved spacetimes generally, and here's where these Mark IV twistors seem to be, I think, the most promising route. We need an independent basis for quantum field theory, etc. The twistor diagram theory basically just takes Feynman diagrams and rephrases them in twistor language. What one would like would be some independent way of generating the twistor diagrams and so on. And it may here be that one takes some ideas from string theory. There is a particular suggestion which was due initially to Michael Singer and developed by Andrew Hodges and myself, when one looks at these sort of string surfaces, but these are actually higher dimensional things. A lot of the ideas come from string theory, but they are complex manifolds of 3 dimensions. They're not membranes, they're things where these are complex manifolds, but at least this is quite a promising possibility for developing an independent approach to twistor diagram theory and other things. Finally, the relation to the UR problem. As yet, one doesn't have any clear ideas as to how twistor theory would apply to the other things I've been talking about today. Certainly the motivations to some extent came from this, the non-locality and description. However, twistor theory has so far been disconcertingly conservative with respect to quantum theory. That is to say, it accepts all the standard rules and dogma about quantum theory without making any genuine new suggestions as to what one should do. Let me just make a remark about Mark IV, since I have it down here. What seems to be a promising idea for how one would look at twistors in relation to general relativity uses the fact, which is already familiar to people who work in supersymmetry theory, that the Einstein equations are the consistency equations for spin 3/2 massless fields. But the other side of this observation is that if you go to flat space, then the charges for spin 3/2 massless fields are in fact twistors. So this tells you that twistors are in a sense intimately related to these spin 3/2 things, and on the other hand, spin 3/2 is intimately related to the Einstein equations. And that link seems to me to be very likely the link that one needs in order to understand how to do twistors in curved space-times. I think that's all I have time to say. Thank you.
If there are questions? Yes?
Curious, you gave an argument which says, I as a person or as a mathematician can do things a computer can't do. And then you proved computers can't do anything and said, since I understand that, I'm better than the computer. Why can't I write a computer program that does exactly the same argument about arbitrary other computers? And therefore the computer says, I'm smarter than all computers because I can understand why other computers can't do things.
The trouble is, you see, that the computer program of itself doesn't have any judgment as to what's true or false. I mean, you can certainly write a computer program.
I mean, I can say the same thing about you.
You don't think I can have a judgment as well, it may be that my judgments are always wrong and so on, but let me make a couple of remarks here. One is that this is a reductio ad absurdum argument. I mean, people sometimes say, all right, well, look, all it shows is that this particular algorithm is something which doesn't decide mathematical truth. one point I should make is I never assume that the human mathematician can solve all problems. That is not part of the argument. All it shows you is that the insights available are not formalizable. Now the thing is that you could say, well, why can't you put this on a computer or something? But the thing is that, I mean, I can obviously can. You put it on a Xerox machine, and that is a particular example of an algorithmic thing, and so on. But that's not really doing what one's doing here. It's the understanding, it's the belief of truth which is involved in this thing. And
I mean, I can't practically, but in principle, I can write a program which understands truth and falsehood, and understands that some things are true and others are false. True, I can modify that program so it doesn't understand truth, but I don't see why I can't have a program in principle that figures that thinks.
Now, what I say is that, first of all, the word understanding, I mean, you use it in a different sense from the way I do, I think. You say that your machine would say yes to certain things and